As Tornado enters squadron service with the German, Italian, and British Air Forces and the German Navy, it will replace a range of aircraft types which had been previously required for the interdiction strike, reconnaissance, and intercept roles. Only Tornado, with its all-weather day-night capability, can penetrate far beyond enemy lines to attack command centers, air bases, and other tactically important targets. This weapon system enables NATO to enforce its strategy of flexible response against any attack from Warsaw Pact countries. The variable wing sweep was chosen as the most practical solution in meeting the range of operational requirements. Wings forward are for takeoff, landing, and long-range cruise. Wings are fully swept for sustained high speed at low-level supersonic flight. The mid-setting is selected for transonic speeds at low level. The fuselage slots have inflated seals representing simple design which proves to be effective even at extreme temperatures. About 5% of the wing area retracts into the fuselage at maximum wing sweep. Since ailerons and spoilers are used as control surfaces, the entire trailing edge is left free for double-slotted flaps. At lower sweep angles, flaps and landing edge slats can be partly extended to give increased combat maneuverability. Fully extended, these high-lift wing devices and Kruger flaps fitted to the fixed wing nib give Tornadoes good airfield performance. Air brakes extension allow for an effective deceleration. Thrust reversers, exceptional for twin-engine fighters, are shown to be highly effective and give rise to shorter landing distances than a brake parachute would do. For very short landings, spoilers and thrust reversers can be pre-armed by rocking the throttles outboard. Deployment is then automatic after the main wheels touch down. Spoilers serve as lift dumpers after touchdown. To be independent of ground supplies, Tornado has an auxiliary power unit, which can be started on internal batteries. It provides the power to run all electrical and hydraulic systems and to start the engines. This allows the aircraft to be held on alert over long periods for immediate scramble. Fuel is supplied via a single NATO connector. This feeds the two fuselage tank groups, wing tanks and external tanks at the fuselage and wing stations. Each tank has an overflow cut-off valve. The refueling process is fully automatic. A retractable flight refueling probe can be fitted to any aircraft. All Tornado tanks can be refueled in flight. Tornado can also be used as a flight refueling tanker. The fairing, which houses the retracted probe, gives no handling limitations, and the performance throughout the flight envelope is unaffected. Turbo Union RB199 engines were specifically designed to match Tornado's range of operational requirements with low fuel consumption. Twin engines provide safety and reliability. For maximum efficiency at reheat settings, nozzles are fully variable. With full reheat, each engine develops more than 67 kilonewton thrust. To give good airfield performance, Mach 2 plus flight and combat maneuver capability. A three-shaft layout enables each section of the engine to run at optimum speed and gives outstanding handling characteristics without the complication of variable compressor stator stages. Modular construction allows units requiring attention to be replaced without the need to return complete engines to the manufacturer for major overhauls. Easily accessible inspection points allow regular health monitoring. The RB-199 was designed to operate on an on-condition maintenance basis and is not removed unless these health checks indicate early stages of failure. Engine changes can be undertaken in the open field by only 3 men. The engines are compact to fit into the small airframe, and large opening doors make installation straightforward. Scheduled time is 3 hours, including run-up. Ease of maintenance has been a major objective throughout the design. The avionics systems are built up on an LRU, or Line Replaceable Unit basis. LRUs are easy to change plug-in modules. Most of them are accessible at eye level. No calibration is needed after installation. BITE, short for built-in test equipment, is fitted to all LRUs. An onboard checkout system continuously monitors the status of the most important LRUs and indicates their serviceability on the central maintenance panel. A reference chart allows the ground crew to identify the malfunction, whether it indicates a go or a no-go situation. For extensive fault diagnosis of the entire avionics system, a special ground test program can be loaded into the main computer via the cockpit voice recorder. Mission data inputs are then indicated on the right-hand TV tab as shown. Approximately 45% of the airframe surface is covered by a total of 430 access panels. The triplex fly-by-wire system allows the realization of a sophisticated command and stability augmentation system, or CSAS for short. The CSAS gives a standard of handling which is unequaled in high-performance combat aircraft. Via potentiometers, the pilot commands are translated into electrical signals. The electrical signals are triplicated for redundancy reasons and are separately routed to minimize risk to damage. At the heart of the CSAS are two computers, one for pitch control, the other one for roll and yaw. Pilot demands, introduced via the control column stick and rudder pedals, are fed into the appropriate computers and combined with signals from pitch roll and yaw rate gyros to give the appropriate commands for controlled surface deflection. Yaw demands are affected by rudder movements. Pitch demands by symmetrical movements to the ailerons. Roll demands by differential movements. At forward sweep angles, roll demands are also fed to the spoilers. The system is tolerant of single failures. If multiple faults occur, a direct electrical link to the actuators is provided. In case of total failure of the CSAS, for example due to battle damage, a mechanical backup linkage will continue to operate the ailerons to provide a get-you-home capability. Thanks to the CSAS, handling characteristics and stick forces are remarkably consistent throughout the range of angles of wing sweep, with the aircraft in clean configuration or with a heavy store load. CSAS damps out the effect of gusts and, combined with a high wing loading, gives a uniquely smooth ride at high speed, low level. In flight, the cockpits are comfortable and unusually quiet, even at high speed, low level. Except for some minor variations, cockpit layouts are common for the aircraft of all three nations. Central feature of the front cockpit is the head-up and moving map display. On the left-hand console, we find wing sweep lever, throttles, hand controller, autopilot, and the CSAS control panel. Engine, fuel, and environmental control panels are to the right. The rear cockpit has two alternative layouts. This is the trainer version with duplicated flying controls and flight instruments. It retains full strike capability. The design of Tornado's avionics system also accounts for effective mission preparation. This includes an electronic map table, which gives rapid, precise flight planning. A cursor is placed over different map positions to designate automatically the mission waypoints, fix points, and targets, which are stored in a computer together with ground speed, fuel, etc. The complete flight plan for a sortie is recorded on the cassette and can be verified by a printed readout. Information stored on each cassette is accepted into the aircraft's computer via the cockpit voice recorder. The data are now being presented on the navigator's left-hand TV tab display in the plan format and show the planned sortie route with present position and time. In flight, Tornado's navigation system is fed from 4 sensors. Their data are optimized in the main computer by a Kalman filtering. Primary sensor is an inter-tail navigation platform providing present position, heading, attitude, and velocity. A secondary attitude reference supplies redundant attitude and heading data, which together with Doppler velocities allow redundant navigation calculation in the main computer. An air data computer gives true airspeed and Mach number. The avionics system provides extremely precise navigation and weapon aiming. It gets an aircraft to the target at low level, enabling a high-speed, single-pass attack in all weather conditions by day or night. The actual navigation information is displayed on the right-hand TV tab in the rear cockpit. At the push of a button, velocity data may be called up. In the center position, the combined radar and moving map display is mounted. This is map only, switched through the range scale 1 million, 1/2 million, and 1/4 million. Radar information only may also be called up. Again, various scales are available. This is the 10-mile scale. Note the resolution, which shows the line of pylons running top to bottom to right of center. Highly detailed radar only on the 4-mile scale shows gravel pits, top left. For weapon aiming or obtained a blind fix, the radar can be ground stabilized. The combination of map and radar information gives high accuracy and good confidence in AC position. The accuracy achieved by this superposition can be seen, for example, at the bridge, top center. Discrepancies can be corrected by the navigator's hand controller. Updated information is inserted into the computer. The main instrument for the pilot is the head-up display. During manual low-level flight, terrain-following radar signals are displayed as flight director commands to the pilot. His task is to fly the aircraft so as to maintain the circular aircraft symbol over the small dot. In the autopilot mode, flight director bars are occulted. With track, height hold, and auto throttle selected, terrain following can be fully automatic down to 200 feet. Radar definition is good enough to register hazards such as pylons, and automatically maintains the preset clearance height, thus minimizing exposure to radar and ground fire. Comprehensive self-test and monitor functions guarantee flight safety upon failure of a component in the system. Height to be flown can be selected, as can a soft, medium, or hard ride, the hard end making the maximum use of cover given by the terrain. For planned targets, the attack is initiated by the navigator. On the weapon control panel, he has pre-selected a weapon package defined by number and type of store, spacing, and fusing. Selection of stores station is automatically performed by the store's management system. One TV tab now shows the attack format. Note Y top left, showing range to target reducing. On the head-up display, the pilot gets the bomb fall line displayed together with the target bar, top, indicating the computer target position. Under bad visual condition, the attack is performed automatically. Under visual conditions, the pilot converts to the visual mode and directs the aircraft so that the marker coincides with the highest target or offset. As the continuously computed impact point crosses the target, bomb release is automatic. Weapon delivery is independent of crosswind, dive angle, and aircraft speed. The target marker H testifies to the system's accuracy. For self-defense, the IDS Tornado has an air-to-air capability. The avionics system includes fire control for air-to-air combat, with guns and the most up-to-date Sidewinder missiles. Each of the two Mauser guns have 180 rounds of 27mm ammunition. Two rates of fire can be selected by the pilot. Tornado was designed to carry a wide range of weapons as specified by the three national air forces. There are 3 under-fuselage pylons and 2 pylons under each wing. The Kuta pair are normally used for ECM pods. This is a typical load: 8 1,000-pound bombs, 2 external tanks, and 2 ECM pods. Alternatively, for shorter ranges, 12,000-pound bombs can be carried. Cormoran is an all-weather sea-skimming anti-ship missile, especially developed for the German Navy air arm. The missile is launched at standoff range outside the range of enemy anti-aircraft weapons. Fire and forget capability is achieved by Cormoran's self-contained navigation system for the early guidance phase and radar seeker head for target acquisition and terminal phase. Cormoran is highly resistant against enemy countermeasures. It attacks at sea-skimming altitudes and impacts just above the waterline. Parallel to the Tornado program, the development of a completely new weapon, the MW-1, Multi-Weapon System 1, against airfields and tank formation was conducted. Weapon delivery may take place in high-speed, low-level attacks. Several 1,000 small bomblets can be released in one pass. Here, in slow motion, the effectiveness can be seen. Covered ground area and density of weapon load can be varied. The empty bomblet containers can be jettisoned for increased getaway performance. Tornado is already one of the most significant weapon systems within NATO, and its effectiveness is still growing with the crew becoming more and more experienced in handling the weapon system as a team.